A guy sends one Bitcoin transaction from his living room. The blockchain, as everyone knows, is pseudonymous. Addresses, not names. The world sees a transfer between two hex strings, and if the guy has done everything right, the trail ends there. Except it doesn't. Somewhere on a server in a data center, an analytics company has just logged his IP address, his approximate city, the timestamp of the broadcast, and the wallet software he's using. They didn't break any cryptography. They didn't subpoena his exchange. They just watched him speak. This is the gap between cryptographic pseudonymity and network-level identifiability. And it's one of the most under-discussed problems in cryptocurrency privacy. Almost every major wallet, almost every major chain, leaks this information. By default, and most users don't even know it's happening. Let me walk you through the mechanics. A blockchain, regardless of which one, is maintained by a peer-to-peer network of nodes. Nodes talk to each other constantly, exchanging blocks, transactions, and metadata. When you broadcast a transaction, your wallet connects to one or more nodes and hands them the transaction, which then flood fills across the network until every node has it. The node you first connected to knows where the transaction came from. It knows your IP address because your IP address is how it routed the message back to you. If that node is run by an honest volunteer with no particular interest in your identity, the leak dies there. If that node is run by a chain analysis firm, or a government contractor, or anyone else who logs first broadcast events, the leak lives forever. And here's the critical part. You do not choose who your wallet talks to by default. Most wallets ship with a short list of predefined nodes they trust. Those nodes are operated by the wallet maker or by the chain's foundation. Some of those entities are trustworthy. Others have partnerships with analytics firms. Many have operational monitoring that produces logs regardless of the entity's intent, that later become legally compelled evidence. Let's look at specific wallet categories. Mobile wallets, the kind most people use, almost never run a full node. They can't. A full Bitcoin node needs hundreds of gigabytes of storage and significant bandwidth. A full Ethereum node needs even more. Mobile wallets instead connect to remote nodes either operated by the wallet provider or by third-party services like Infura for Ethereum or Blockstream's liquid infrastructure for Bitcoin. When you use MetaMask, for instance, your wallet is by default calling Infura servers for every transaction, every balance check, every interaction with a smart contract. Infura sees your IP address, linked to your wallet address, linked to your activity. Infura is owned by Consensys, a major Ethereum ecosystem company. Their logs have been subpoenaed before, and they comply with legal process. Desktop wallets vary. Some, like Bitcoin Core, run a full node by default, which means your wallet talks directly to the peer-to-peer network rather than through an intermediary. That's better in principle. It's also slower to set up, and most casual users never get there. Other desktop wallets, like Electrum, are lightweight and connect to public servers operated by volunteers. The servers see your addresses and your IP address because the SPV protocol used by lightweight wallets exposes both. Hardware wallets are often misunderstood in this context. A ledger or Trezor secures the private key, which is important, but the hardware wallet does not handle network communication. The software that talks to the blockchain is Ledger Live or Trezor Suite, or whatever third-party wallet you've paired with the hardware device. That software leaks your IP address just like any other wallet software would, because that's the layer where the leak happens, not at the key storage layer. Let me describe what the actual telemetry looks like from an observer's side because the abstraction can obscure the impact. An observer running a set of well-connected Bitcoin nodes can watch for first broadcast events. When a transaction appears on the network, they note which of their peers announced it first. If that peer is not one of their nodes, they note the IP of the peer. Over time, they build a database of transaction-to-IP associations. For a specific transaction, this is probabilistic. For a user who broadcasts many transactions from the same IP over weeks or months, the correlations become statistically overwhelming. A paper from 2014 by Biryukov, Kovratovich, and Pustogarov formalized this attack. They demonstrated that on the Bitcoin network at the time, they could de-anonymize a significant fraction of users by operating a modest number of well-placed nodes. The attack has been refined in the decades since, and chain analysis firms have industrialized it. Ethereum has a similar issue, with some differences. Ethereum's transaction propagation is faster and denser, which reduces the window for first broadcast attribution. However, Ethereum's architecture puts heavy reliance on hosted RPC endpoints, because most users interact with dApps through browser-based wallets. Every interaction with a decentralized application routes through a node. Those nodes log. The typical Ethereum user's IP is exposed to multiple third parties per session, because they're constantly fetching state and constructing transactions through external services. Now let me talk about the exceptions, because some wallets and some configurations do address this. The first defense is running your own node. If you operate a full node for whichever chain you care about, your wallet talks to your node, and your node talks to the peer-to-peer network. The observer watching for first broadcast events sees the transaction originating from your node's IP. That's still your IP, unless you've hidden it, but it's no longer tied to a wallet service that logs your activity. You've cut out the middleman. The second defense is routing your wallet's network traffic through Tor or a privacy-preserving VPN. Several wallets support this explicitly. Bitcoin Core can be configured to use Tor for all peer-to-peer communication. Wasabi Wallet and Samurai Wallet route everything through Tor by default. Electrum supports a Tor proxy setting. When you use these configurations, the IP that your wallet presents to the network is a Tor exit node, not your home IP. The first broadcast attacker sees an exit node, which is shared among many users and provides plausible deniability. The third defense is transaction-level privacy techniques that operate within the chain. For Bitcoin, this includes CoinJoin implementations, which combine your transaction with many other transactions in a way that obscures which input-output mapping is yours. The technique was formalized by Gregory Maxwell, building on Chaumian mix principles. And modern implementations like Wasabi's Wabi-Sabi protocol or Whirlpool from Samurai have made it practical. CoinJoin doesn't hide your IP at broadcast time, but it does break the on-chain linkage between your deposit address and your eventual spend, which is the other half of the privacy picture. For Ethereum, the situation is harder. The account-based model of Ethereum makes mixing more complex, and privacy-preserving smart contracts like Tornado Cash have faced significant regulatory pressure. Zero-knowledge rollups and L2 privacy solutions are emerging, but the ecosystem is fragmented. For most Ethereum users right now, IP-level privacy is the first and most impactful layer, because on-chain privacy on Ethereum's mainnet is largely unavailable in practice. Now let me address a common misconception. Some users believe that using a hardware wallet is enough to be private. It is not. A hardware wallet prevents your private key from being extracted by software malware. It does nothing to hide your IP address, your transaction patterns, or your behavioral fingerprint. Privacy and security are different properties. You can have one without the other. Most users have neither, despite believing otherwise. Another misconception involves exchanges. Some users think that because they only send crypto to or from a single exchange, their privacy is limited to what the exchange knows. This is almost true, except that the broadcast of the transaction from your wallet still leaks your IP separately from the exchange's records. If the exchange then gets breached, and analytics firms have also been logging first broadcast events, the correlation becomes even richer than either source alone. The practical takeaways for someone who cares about this. First, understand that IP-level privacy is a distinct problem from on-chain privacy. Solving one does not solve the other. Plan for both if your threat model demands it. Second, evaluate your wallet's network behavior explicitly. Read the documentation. Find out what servers it connects to by default. Check whether it supports Tor or a proxy. Assume that any wallet without explicit privacy networking is leaking your IP to known third parties. Third, consider running a node if you transact meaningfully on a specific chain. It's more work than most people want to do. For those who stay with it, the privacy improvement is real, and the educational value of running a node compounds. Fourth, if you use a mobile or browser wallet, consider routing your device's traffic through Tor or a privacy-preserving VPN for the session in which you transact. This is a blunt tool, but it defeats the naive version of the first broadcast attack. Fifth, minimize the surface area. If you only transact a few times a year, the privacy cost of using a convenient wallet is lower than if you're transacting daily. Match your tooling to your actual usage pattern. There's a deeper theme here that applies to privacy in general. Every layer of a system has its own privacy properties, and assuming the strongest layer defines the whole system's privacy is a mistake. Cryptocurrency was designed to be pseudonymous at the ledger layer. At the network layer, it was not designed for privacy at all. The peer-to-peer protocols that carry transactions were built for reliability and openness, not anonymity. That trade-off was reasonable at the time of Bitcoin's invention. It has not aged well for users who assume the word blockchain implies full privacy. The real privacy story, in 2026, is not about choosing a privacy coin and calling it done. It's about understanding which layer of which system is leaking what, and applying targeted mitigations at each layer. Your IP leaks a broadcast. Your address linkage leaks at the ledger. Your identity leaks at the exchange. Each leak has its own defense, and you choose which to apply based on what you're actually defending against. If you want a walkthrough of setting up a Bitcoin Core node with Tor and configuring a wallet to use it, let me know in the comments. That's the foundation for anyone serious about IP-level privacy on Bitcoin. And if you want similar coverage for other chains, tell me which ones, because the specifics differ significantly, and the one-size-fits-all privacy advice you'll find elsewhere tends to be wrong in all the important ways. Your wallet is probably talking to people you didn't know it was talking to. Find out who. And if you don't like the answer, change the configuration. That's the entire privacy practice in one sentence. It just takes effort to do at every layer.